introduction. I'm Shotaro, postdoc at the NTHU in Taiwan. I talk about today maybe your previous talks by Tetsuya and Kaya talk about birth and main issue and general issues. I talk about specific science study by Chan. Okay. So introduction, I think I should skip. It's already done. But FRB, I'm studying FRB, and it's interesting just because its origin is still unknown, and it's very new, and it has many applications. And the most important thing I would emphasize here is some sources show repetition, however others don't. So we call repeating FRB population repeaters, and not repeating population non-repeaters. When I say not repeating, we already detect one burst from FRB position. However, we don't see any more. We call this kind of source non-repeater. Then also, one of the most important questions would be, do all FRB population repeat or not? So the answer is already, we know the answer, no, so far. Actually, Canadian hydrogen intensity mapping experiment, so-called CHIME, already introduced. This Canadian telescope already discovered apparently the fraction of repeating population is about a few percent. This is tiny fraction. So most FRB sources do not show repetition. So this is just an example obtained from this CHIME telescope. And for different directions, they found a consistent number of a few percent. However, this is just an apparent fraction. And in this talk, I explain the true fraction of repeating population would be completely different. I explain why. So we have actually two observation biases. The one is classification problem. So this is showing observed population of repeating and non-repeating FRB. And naively speaking, we can expect each population can have a different origin. Like repeating population can be probably explained by magnetar-like model. Magnetar can repeatedly produce radio bursts. However, on the other hand, non-repeating FRB can be explained by other kind of catastrophic event, which only produce one burst at the end of death, at the end of their life. For example, binary compact star merger, for example, or massive star collapse into black hole. This kind of model can produce non-repeating FRB population. However, the situation is not so simple because magnetar produce radio bursts. If they are isolated pulse, this can be also misclassified as non-repeating FRB. Therefore, there are two channels, at least two channels, to create non-repeating FRB. So, what we know here is we know this is a few percent only observationally. However, we don't know what's going on behind this, how they have a complex origin. So this is the issue. So as I said, same observation repeater. These are repeating bursts. If you have a different time window of observation, this observation can only find kind of one burst, and this is non-repeater apparently. However, another observation having different time window can result in discovery of repeater. Therefore, same source can have a different classification at different time. Therefore, classification is observationally very incomplete, and in general, true fraction of repeater is much higher than apparent repeater fraction. This is very clear. The second problem, observational bias, is in case of CHIME, also bursts actually. This is a cylindrical shape and extending north-south direction. Therefore, they have a dependence. Exposure time has a dependence on declination angle. And if you go to the North Pole, it has a longer exposure time. But if you close to the equator, the exposure time is 100 times or even more smaller. Therefore, this kind of non-uniformity on the sky kind of may be difficult to assess the detection rate of burst as a function of time because the exposure time fraction is not the same. So these two problems is kind of what I want to solve in this talk. So I need to collect observation. So this is a strategy. So first, how to classify FRB. So we consider time-dependent classification. So this means if first occur, this source is recognized as a non-repeater and until the second burst. And then we count one non-repeating source here until second burst. And after second burst, this source turns into repeater now. So we count one repeater, but we reduce one. This is not our non-repeater anymore. So we kind of count it as 0. So this kind of switch, temporal switch happens in this classification. And this is well-defined classification observation. And the second point is we solve the problem of non-uniformity of the exposure time by considering, for each source we consider on-source time fraction, exposure time over entire operation time. This is different for different FRB. We take into account this fact when counting FRB number. This can solve this problem. Then let's look at the result of observation. So this is not a model, this is purely observation. What I'm showing here is kind of result when I use chime observation. So I use about 400 bursts detected by chime during this period. And what I'm showing here is x-axis is operation time of chime from observation, since observation start. And the top panel shows cumulative source count as a function of time. And this is the non-repeater, and this is repeater. The bottom panel is the same figure, that just showing average detection rate. So it's the same thing in a different way. And we found for non-repeating population, interestingly, this is the first time we see, if you look at the average detection rate, we have a kind of significant decrease over time. This is statistically significant, and this trend is discovered for the first time. And this is seen after 1,000 hours of observation. And this already have an implication for theory, because if all the FRB population is truly non-repeater, like binary neutron submerger or whatever, only one-time population, then the detection rate should stay the same. However, this is decreasing. Therefore, we can already say this cannot be explained by a true non-repeater alone. So this is one implication. The second is maybe this decrease is produced by the appearance of repeater here, because there is a temporal switch from repeater, non-repeater to repeater. This decreases the non-repeater number. So this can be also read from this observation. And also, in the meantime, repeater detection rate stays almost constant. So maybe this implies repeater have a different, each source has a different repeating rate. Maybe repeating rate have some distribution. So this is the implication, and then we want to model this more quantitatively. So we consider a simple model of two populations. One is repeating population, the other is non-repeating. And for repeating population, we assume 4 parameters regarding repetition characteristics. I don't talk about the detail, but 4 parameters. And for non-repeating population, we can consider only 1 free parameter. Then in total, we have 5 parameters, and we can compute this expected number for apparent non-repeating FRB and the repeating FRB from the source. So this is a schematic picture of the model. Then this is the MCMC result after fitting the observed source count. Then we have 4 population, 4 parameters for the repeating population and 1 parameter for non-repeating population. So I skip this, but this is the result. This is a figure, same figure as previously I showed. X-axis is the chime operation time, y-axis is the source count evolution. And these black point, these are observation, and I fit this with model, simple model. And actually this blue solid curve show the apparent non-repeater from repeating population. So this is kind of contaminating source. And this repeater is just coming from repeater. in between these two, there is a solid dashed line here, dashed blue line here. This is actually upper limit on the true non-repeating population. We set upper limit from the fitting procedure. This means this is repeater fraction, true repeater fraction. So true repeater fraction means this is not apparent fraction, but the true repeating fraction. And we have the upper limit for true non-repeater, therefore we have a lower limit for this fraction. And our result revealed for the first time that the true repeater fraction is exceeding 50%, even reaching 100% with some uncertainty. And this is actually very different, much larger than apparent value of time observation. Apparent value is only a few percent, but maybe all population can be repeating population. This is the implication. And this also at the same time means we discussed 400 FRB, that more than 200 FRB source can be actually repeater. However, we only know 50 sources, which is confirmed as a repeater so far. So this is the kind of result. I go to the implication. So another implication is, interestingly, this is showing the distribution of repeating rate. Pink region, this is already discovered child repeater. And this yellow region, this is what we discovered in this work. And our discovery showed actually the typical repetition rate of majority of population is actually much lower than what we see in observed repeater. This is about only one burst over 3,000 hours. And therefore, we reveal there is a hidden population which is not detected yet, and will be detected slowly in the future. So this is the discovery, and this implies there should be hidden population of huge repeating sources. And we also need to explain this theory. So this is the implication, and I stop here. This is our conclusion. Thank you so much.